All right, let's go ahead and get started. I want to welcome you back to Unit 6. This is nomenclature. We are naming chemical compounds of all types, covalently bonded compounds. We've taken a look at simple ionic compounds, that's binary ionic compounds. We've looked at compounds involving transition metals, and now we're looking at ionic compounds involving polyatomic ions. But as we do that, I want you to be sure and mix these up. In other words, I'm going through one section at a time as I move through these notes, but I want to get because I want to give you multiple exposures, multiple practice with each type of nomenclature. But it's important for you to be able to take a chemical compound out of the blue, where I give you a formula. It's not in any context. It's not in a section titled covalently bonded compounds or whatever the case may be, and be able to name that compound from a formula or vice versa. So although we're looking at this from a standpoint of individual types of nomenclature, I want you to be able to, at some point, practice with these compounds in a mixed bag, okay? So here we go. We're going to be needing a polyatomic ion chart for this one. So if you don't have one handy, go ahead and pause the video and we will get started. So ammonium chloride would be the first one because we've got the polyatomic ion NH4Cl. Remember that NH4 is one of the few positively charged polyatomic ions. It's NH4. I'll just do a couple here for you and then I'll let you go on your own. NH4, remember, has a charge of +1. From the polyatomic ion chart, I know that. Cl has a charge of -1. So when I do the switch, I get NH4Cl. So remember, if I give you the formula, you don't have to worry about that. All you have to do is name it. But you do have to recognize that this NH4 is a polyatomic ion. All right? Okay, so that takes care of the first one. Let's look at the second one. We've got strontium, and we've got something called, or something that's NO3. That's nitrate. NO3 is nitrate. So this would be strontium nitrate. Remember that the charge on the strontium is +2 because it was in the second column. Nitrate has a charge of -1. So when we do the switch, we get SrNO3 in parentheses 2. Now, can I remove the parentheses and say SrN2O6 like I might do in math? You distribute the 2? No, absolutely not. These are 2 units of NO3, 2 distinct units that you cannot distribute the 2. So that would be strontium nitrate. So that takes care of the first 2 for us. The next one would be lithium hydroxide. Recognize that hydroxide is a polyatomic ion having a charge of -1. So lithium hydroxide for the next one. The next one would be calcium carbonate. Calcium carbonate for the next one. The next one, typo right here. If it's not correct on your paper, it should say NaNO2, just like that. Let me fix that on my paper. So we've got NaNO2 would be sodium nitrite, okay? NaNO2 would be sodium nitrite. The next one would be KClO3, that's potassium chlorate, ClO3 being the polyatomic ion chlorate with a charge of -1. So when you do the switch with the +1 of the potassium, you get +1 and -1 canceling away. And then the last one we've got is NaHCO3. HCO3 is bicarbonate, so this would be sodium bicarbonate. Sodium bicarbonate for that one. All right, let's reverse this process now. I'm going to give you the name and you write the formula. All right, potassium carbonate. How would we write that? Well, remember that potassium has a charge of +1. Carbonate has a charge of, carbonate is CO3, and it has a charge of -2. I'm going to write it this time this way. All right, I can do it either way, -2 or 2-, but I want to write it a different way this time. When I do the switch, though, here's what I get. I get K2CO3. Do I need parentheses around the CO3? No, because there's a 1 subscript there. I don't need it. I could have put it, but it doesn't change anything, okay? So K2CO3 for that first one, and there we go. The next one, magnesium sulfate. Magnesium has a charge of +2, sulfate a charge of -2. So when I do the switch, they just cancel away, and I'm left with MgSO4 for magnesium sulfate. The next one is aluminum acetate. Aluminum acetate is Al for the aluminum, and acetate is, let me look that up, it's C2H3O2. It has a charge of -1. So when I do the switch, I get Al, and then I need the parentheses this time. I've got to have them for the 3 subscripts. So we have C2H3O2, 3, just like that. Sodium hydrogen sulfate, all right? Hydrogen sulfate being HSO4 has a charge of -1. So when we do the switch, we get NaHSO4, and that one's done. Next, calcium phosphate. Phosphate is one of the few polyatomic ions that has a charge of -3. This one has a charge of -3, so when I do a switch, I get a 3 right there. Calcium, of course, is +2. It's in the second column of the periodic table. One of the alkaline earth metals. When I do the switch, I get Ca3PO4 2. Yes, those parentheses have to be there. The same thing is true of ammonium sulfate. The next one, those parentheses have to be there because of the fact that we have a 2 subscript right there. So ammonium is +1, but SO3 is -2. When I do the switch, that 2 is it's the subscript after the NH4. It's got to be there. And the last one is barium hydroxide. +2, -1. When we do the switch, the parentheses have to be there because that 2 cannot be distributed. That's barium hydroxide. Barium hydroxide. All right. So let's take a look at these. Ionic compounds, this time involving transition metals. Transition metals. Remember, those are the ones in the center of the periodic table that have multiple, usually have multiple charges. CuCl could have been +1 or +2, but it's +1. How do I know that? Well, here's how I know. If Cl has a charge of -1, and there's a 1-to-1 ratio of Cu to Cl, that means that the Cu had to have a charge of +1, right? It had to have a charge of +1. So when I do the switch, I get CuCl. So that means that the charge must have been a +1. So I've got copper, Roman numeral 1, chloride. Let's compare that, though, to this next one. This time I have 2 Cl's, right? I've got 2 chlorines this time. So this time, when I write the formula, Cl has a charge of -1, but there's 2 of them. So when I do the switch, this 2 must have come from here, right? So that means the charge was +2. So this time we write copper 2 chloride just like that. Copper 2 chloride would be the second one. The next one is tin 4 fluoride. The reason is fluorine has a charge of -1, but there's 2 of them. And because there's 4 of them. 4 times -1 would be -4. So tin has to have a charge of +4, right? So we write tin 4 fluoride like that. Let's compare that to the next one, which is tin oxide. But because the charge on tin this time has to be +2, because oxygen is -2, it's in the 16th column, we get tin 2 oxide just like that. Okay? Now, by the way, let me stop here and make a notation. And that is, there are some elements on the periodic table, transition elements, that do not have multiple oxidation number possibilities. So you have to look at a periodic table that shows which ones have them and which ones don't. There are a few that don't have them. If an element does not have multiple oxidation possibilities, this is important. If it doesn't have more than one transition or more than one charge possible, then you do not write the charge in the name with the Roman numeral. And if you do, it's wrong. Okay? If you do, it's wrong. Okay. So the next thing is this: iron and sulfur. Iron is -2. That means that the iron must have been +2. So we get iron 2 sulfide just like that. We've got HgO. This is mercury 2 oxide because oxygen is -2, so the mercury must be +2. The next is H2S. So this time, since sulfur is -2, that must mean that the mercury is Roman numeral 1. So we have mercury 1 sulfide just like that. The next one is iron +3 oxide because that 3 must have come from there. So +3 is the charge on iron 3 oxide. We'll put that right there. The next one, the last one is CrN. We have chromium 3 nitride. Chromium 3 nitride for that one. I want to repeat one more time. If the transition metal does not have multiple possible charges, you do not write the charge with Roman numerals. And if you do, it's wrong. Okay? If you do, it's wrong. All right, let's take a look at these. Write the formula from the name. We have iron 3 chloride. So I know the charge on the iron is +3. So I'm going to say iron, Roman numeral 3, chlorine, or chloride I should say, -1. When I do the switch, what do I get? I get FeCl3. FeCl3. So that's the first one. Let's take a look at another one. Okay, tin 4 oxide. Now this is a little bit trickier. Tin, I'm told, has a charge of +4, but oxygen has a charge of -2. Now when I do the switch, here's what I get. I get SN2O4. But remember, I have to reduce these, right? This is an ionic compound. I have to reduce these. So I get SNO2, right? I divided both by 2. So SNO2, not SN2O4. Remember, you do have to reduce these, right? You do have to reduce them. All right, let's move on. We've got copper 2 sulfate, CuSO4 for the next one. Sulfate has a charge of -2, so it'll cancel with the +2 on the copper. Manganese, Roman numeral 4 oxide, we have MnO2. Lead 2 nitrate, PbNO3 open or parentheses 2. Yes, those parentheses have to be there. Next, chromium Roman numeral 2 hydroxide, CrOH2. Next is cobalt 3 sulfide. Remember, the cobalt now has a charge of +3. Sulfur has a charge of -2. When I do the switch, I get CO2S3, just like that. All right. We want to finish this up now with the naming of acids. So here we go. How do we name acids? Well, what are acids? Well, we'll have a whole unit on acids later on, but we need to know how to name basic acids right now. Here are the rules. We're gonna separate acids into those containing oxygen and those not containing oxygen. All right. So since all these acids have the same cation, and by definition, acids have hydrogen ions. Okay, they're H+. We don't need to name the cation. The acid name comes from the root name of the anion name. So a prefix of hydro and the prefix of it and the suffix of ic are then added to the root name of the anion. Now that sounds complicated. It really isn't. Let's look at a simple example. Let's just say we have HCl. This would be called hydro because there's no oxygen there. We call it hydrochlor because of the chlorine ic acid. Hydrochloric acid for HCl. HCN would be called hydro because there's no oxygen. Hydrocyanic, okay, because CN is cyanate. Hydrocyanic, and then acid at the end, just like that. Hydrocyanic acid. Now, if it contains the element oxygen, all right, if it contains the element oxygen, then we name it a different way. Since all these acids have the same cation, we don't need to name the cation. The acid name comes from the root name of the oxyanion or the central element of the oxyanion. Again, it sounds complicated. It really isn't. We're going to take a look at some examples. Suffixes are used based on the ending of the original name of the oxyanion. If the name of the polyatomic ion ends with ate, we're going to change it to ic for the acid, and if it ends with ite, we're going to change it to us in the acid. So let's take a look at these examples. HNO3, which contains the polyatomic nitrate, is called nitric acid, but HNO2, which contains the polyatomic ion nitrite, becomes nitrous acid, just like that. And we're going to end this with the very simple technique of naming bases. It's very, very simple. We simply name the cation and then add this ending, hydroxide. So NaOH would be sodium hydroxide. NaOH, sodium hydroxide. Barium hydroxide would be BaOH2, right? BaOH2 is barium hydroxide. Folks, that's going to end it for this screencast, and that'll finish us up for Unit 6, Nomenclature. If you need to review these videos, go ahead and go back, but remember to mix them up. Don't look at them from the standpoint of all of one type, all right, because you won't see those on exams or quizzes in that way. So I'll see you in the next one. Thanks. Bye-bye.